Thanks so much. Yeah, I want to say, first of all, a big thank you to the organizers and the Institute for having me here. Very exciting for me, huge honor. And thanks for all of you coming to see me. That's nice. So the plan for today is to talk about the Tambara Affine line. It's all right on the board. This is also the title of the preprint that you can find online. And it's joint work with, I'm trying to get these in order. So David Chan is here. David Maroney. Completely. And Daphne. Great. Okay, so that's the title. Those are the people. There's also me. And I'd also like to give it a joke title. It's Spectral Elevators. Subtitle: Going Up for Ghosts. Great. Okay, hopefully all of the words on the board will become clear eventually. But I should start really with this one. What's the word Tambara indicating? Right. So let's get into it. The Tambara Affine line refers to a Tambara functor that we call the affine line. And what is a Tambara functor? A Tambara functor, I should have listened to the instructions about the board. A Tambara functor is some kind of generalization of a commutative ring, or really a generalization of a commutative ring with G action. And so throughout this whole talk, I'll have fix some finite group G. And later, I'll fix it to be a particular group. But for now, it could just be any finite group. And the data of a Tambara functor consists of a bunch of commutative rings and a bunch of functions between the commutative rings, satisfying a bunch of axioms. So let me sort of give an example picture of what this might look like. If I have a Tambara functor T, this consists of a bunch of commutative rings, one commutative ring for each subgroup of G. For each subgroup of G, I get a G set called G mod H, and for each of those G sets, I have a commutative ring T. So there's a commutative ring for each subgroup of G. And I might have more than one subgroup of G, as often happens if G is not the trivial group. And in that situation, when I have two subgroups of G, where one is contained in the other, I get three interesting functions happening here. There are, so here for, let's say, K contained in H, I have one function here denoted restriction, which I'm going to write RES. There's a function here called transfer, which I'm going to write as TR. And there's a function here called norm, which I'm going to write as NM. Okay, and so far these are just functions between the commutative rings, not necessarily ring homomorphisms or anything like that, just functions between the underlying sets. But there are a whole bunch of axioms about these functions. So in particular, one of the axioms says this restriction map is always a ring homomorphism. But interestingly, the transfer map is not, the norm map is not. So there's all these complicated axioms, but maybe a few key ones to understand. The restriction map is always a ring homomorphism. The transfer map is not a ring homomorphism, but it will be additive, it preserves addition. And the norm map is also not a ring homomorphism, but it is multiplicative, it preserves multiplication. Okay, and in addition to this data, there's a little bit more going on. Also at each level, I have an action of the Weil group of the corresponding subgroup on the commutative ring. So at level K, I have this commutative ring T of G mod K, and it's acted on via ring automorphisms by this group normalizer of K mod K. All right, that's part of the data of the Tambara functor, and also these actions have to satisfy certain properties, and I've also left out some more data, but this is the basic kind of picture. There's a bunch of commutative rings, a bunch of maps between them, a bunch of axioms about how those maps behave, and like I said, the upshot is that these objects, these Tambara functors, generalize commutative rings in some sense. And so let me give you one way in which that's true. So I have the category of commutative rings, or I could even take the category of commutative rings with a G action, and I can produce from any commutative ring with a G action a Tambara functor, a G Tambara functor. And the way this construction goes is I take a commutative ring with G action, and I produce this guy that I call Fp of R, Fp for fixed points. And what does this Tambara functor do? The data of this Tambara functor is a bunch of commutative rings, one for each subgroup of G. When I plug in a subgroup K, what I get is the ring of K fixed points inside R. R has an action of G, K is a subgroup of G, so there's a subset of R which is fixed by all the elements in K. That subset is a ring, it's a commutative ring. I can assign that at each level. And what happens in between the levels? I've done my picture upside down from what I had before. I should fix that. Okay. R, K. Between the levels, I'm supposed to have these restriction maps, these transfer maps, and these norm maps, and this vial action. But let's just focus on these maps for now. The way this works, this restriction map is an inclusion. In this picture here, K is contained in H, so being fixed by H is a stronger condition than being fixed by K, so this is a subset of this guy. And that inclusion is a ring homomorphism, good stuff. And this map here, the transfer, what does that do? I take something in the K fixed points, and I sum together some vial conjugates, and I get something in the H fixed points. This is the trace map from Galois theory that you might have seen. If you learned about the trace map in Galois theory, it is a special case of this exact construction. You look at the different fixed points of your extension field, and between those fixed point levels, I have inclusions, and I have this trace, and I have this norm in Galois theory. And those give me exactly the same formulas to define the transfer and norm in these Tambara functors, these fixed point Tambara functors. Okay, so that's some kind of construction. It takes a G ring, gives me a G Tambara functor. This is a functor from the category of G commutative rings to the category of G Tambara functors, and this sits nicely inside here. This category of G Tambara functors is really truly just a bigger category than this guy. Okay, so what's the point of what I'm talking about today? We have these objects called Tambara functors. We care about them for a few different reasons, but maybe one reason you've heard before is that if you have a sufficiently nice commutative G-ring spectrum, where sufficiently nice means something very specific, then if you take pi 0 of that ring spectrum, it has naturally the structure of a Tambara functor. The pi 0, you can look at pi 0 of the underlying spectrum or pi 0 of the fixed points. That gives you a bunch of commutative rings, and they will come nicely equipped with these transfer, restriction, and norm maps, and these actions of these vial groups, and all the axioms will be satisfied. So these show up in equivariant homotopy theory, and it'd be nice to understand them as algebraic objects. These are algebraic invariants that we produce that are different from things like abelian groups and commutative rings and whatever. There's a different algebraic theory with different theorems that apply, and we're able to make a lot of progress in homotopy theory traditionally because we can do things with abelian groups and modules and commutative rings and so on. So when you produce algebraic invariants that have the form of an abelian group, you have lots of tools for studying that algebraic invariant. And so the goal of this kind of work is to say, can we try to build up our understanding of the category of G Tambara functors so that we can deal with these objects in a way that is less piecemeal, where you don't just like produce one algebraic invariant and then just like try to think really hard in a different way in each special case. It'd be nice to have some general tools for understanding the category of G Tambara functors. Okay, so I'll stop mentioning motivation for the rest of the talk. Hopefully you just have to believe me that this is kind of fun to do. That's my actual motivation. And the thing we're going to talk about is trying to do some kind of algebraic geometry with these Tambara functors, because I mentioned that a Tambara functor is supposed to be some kind of generalization of a commutative ring, or some kind of generalization of a G commutative ring. And the whole point of commutative rings maybe is that you can do algebraic geometry. At least a really fun thing you can do with commutative rings is algebraic geometry. And so it'd be great to do a similar story here, to have some kind of notion of commutative algebra and algebraic geometry for Tambara functors. But if you imagine that you had never learned any algebraic geometry before in your life, trying to prove all the theorems from scratch is like kind of annoying. We have the huge advantage that people have done algebraic geometry before. So we know which theorems to look for, and we know which proof techniques might work. And that surely was the key to our success here. So I'll try to explain what sorts of concepts did we think about, what results did we get. Maybe I'll just switch boards, but this can stay up for a bit. We'll probably return to this a little bit later. Okay, so if you're trying to do algebraic geometry or commutative algebra, you're starting with commutative rings. The first thing you have to do is understand what are prime ideals, because you want to understand spec of a commutative ring, which is a space whose points are prime ideals. So I'd like to have some construction that takes a Tambara functor and produces some kind of spec of that Tambara functor. And this construction is due to Nakaoka. Defined this topological space, spec of T, for any Tambara functor T. Again, we're fixing a finite group, so sort of story depends on which group you're using, but for a fixed finite group, there's always a construction that takes a Tambara functor T, produces spec of T. This is going to be a topological space, and the elements in this space, the points in this space, are prime ideals of T, whatever that means. And so I'll tell you what that means. So what is an ideal? The easiest way to say what is an ideal is that I have a morphism of Tambara functors from T to T prime, and then I look at the kernel of that morphism. In commutative rings, that gives you the notion of ideal. Okay, but I should tell you what is a morphism of Tambara functors, because I haven't done that yet. And so now I'm going to switch boards again. Right, so here is the data of our Tambara functor T. And I could have another Tambara functor T prime, which again has a commutative ring assigned to every subgroup of G, and also in action at each level by the Weil group, all the same data. And a morphism from T to T prime is just a bunch of ring homomorphisms. These horizontal maps are going to be ring homomorphisms between the corresponding levels that make all the structure maps, respect all the structure maps individually, is what I mean to say. So if I do restriction and then I move over, it's the same as moving over and then doing restriction. Or if I did transfer and then move over, it's the same as moving over and then transfer. Okay. And also they need to be compatible with these actions. It's the thing you would expect. Okay, great. So if I have a morphism of Tambara functors, I can look at the kernel of that morphism. And what I mean by that is you look at each level individually, you look at the kernel of this ring map, that gives you a set. And that collection of sets is what I call the kernel of S. And collections of sets that arise of the kernels of morphisms between Tambara functors, those are called ideals of Tambara functors. That's all it is. They will be, because these are all ring maps, they will be level-wise collections of ideals. But there's more structure than that. Okay. So anything that arises in this way I call an ideal. You can also characterize this internally, but I think this is easier to say. And great, so now I know what an ideal is. What does it mean to be prime? If, let's say, P is an ideal of a Tambara functor, this ideal is prime if and only if, well, first of all, I need P to not be the entire Tambara functor. That's a classic restriction. And then also, if a product of two ideals is contained in P, then one or the other is contained in P. If you wrote down this definition for commutative rings, it would give you exactly the notion of prime ideal. And so we're going to write down the same definition for Tambara functors, and we're going to call that prime ideal. You have to not be the entire Tambara functor, and you have this condition about containing products of ideals. And to be clear, the product of two ideals, what do? You take your two ideals, which is a level-wise collection of sets. You take these are level-wise collections of ideals. You take the level-wise product of those ideals, and that gives you a collection of sets, and you generate a Tambara ideal from that. Okay, so it's a bit complicated, but at least visually the definition looks very much like the definition of prime ideal in ordinary commutative algebra. And so then you can define this space, spec of t, which has points that are prime ideals. It has closed subsets that are defined in exactly the normal way for the Zariski topology. It's a very nice space. It has good properties. Cool. So we're happy with this construction, but we'd like to compute it sometimes. And there hasn't been a ton of progress on that front. So maybe the prior work I should mention is also due to Nakaoka for cyclic groups of prime power order. We know the structure of spec of what I'll call A underline. I'll describe what this guy is in a sec. And also work of Kajier-Gannett tells us for arbitrary cyclic groups, we know spec of A underline. And what is this A underline? This A underline is the initial object in the category of Tambara functors. For whatever your group is, there's an initial object in the category of Tambara functors. So for commutative rings, the analogous thing would be the ring of integers that's initial in the category of commutative rings. And so this guy, A underline, behaves a lot like the integers in the category of Tambara functors. And it's good to understand what is spec Z, right? We did that a long time ago, back in grade school when you learned about prime numbers. And that's really, paid off well for us ever since. So it's a good thing to understand. And next up in commutative algebra, what you might want to do, so, classically, what does this correspond to? This corresponds to understanding spec of Z, which algebraic geometers would call A0, the affine point. Okay, so it'd be really cool if we were doing algebraic geometry to be able to figure out A1, which classically is like spec of Z adjoint T. And right, that's the title of the paper. It's about the affine line. Okay, so we're going to talk about how we approached that problem. Also, I should mention, if there are questions at any point, if you feel like I've said something confusing, or if I haven't said something confusing, but you want me to say something else, or if you want to say something without me responding, I guess that's also fine. It might be a little rude depending on what you say. Just let me know. Okay. Yeah.
Questions at this point, but maybe that's your goal.
That's what I asked for, yeah.
So one is, so you could, you said the spec T is a space. You could also level-wise form spec of your things.
Yes.
Visual rings, and there's some kind of
it's a great question.
diagram of what's the relationship there?
Yeah, it's a great question, right? So you could level-wise, at each level you have a commutative ring, you take spec of those things, I get a space at each level. These restriction maps are ring homomorphisms, I get maps the other way on spec, and you might think, oh, there's a nice, it's something like a path through this picture would give me a prime in T. But no, the really bad news is that when you have a Tambara prime ideal, each level will be an ideal, but usually those levels are not prime. So there's not a good story that I know of just in terms of specs of the individual levels. Yeah, but thanks. Yeah, please.
There's also the functor that T represents.
Yes.
Can you say anything about that?
I would love to. We will. Yeah, absolutely. It's really interesting to think about the functor that T represents on the category of Tambara functors, and we'll see. We'll have some representable functors showing up in a second. For this guy, Z adjoint X represents a really good functor, and we'll do the analogous thing. But more general thought about trying to do like functor of points approach to Tambara algebraic geometry, I don't have a lot to say about right now, but I would love to talk about it in general. Yeah. Okay, cool. Right, so the dream for us was that classically we know about spec Z, it's the primes and also 0. And in more recent work, we know about spec of A underline, at least for a large class of cyclic groups. And we'd love to have some understanding here. Can we go from A0 to A1? Can we understand the structure of the affine line? And I should say, classically, we do know spec of Z adjoint T. you can write down an explicit description of every single prime ideal of Z adjoint T. You can completely understand the closures of every point. We have a good picture. It's famously in the red book. It's like this very confusing picture if you ever start to learn algebraic geometry and they say, here's a picture of the affine line, and it's two-dimensional, and you look at the picture, and there's like all these curves going through it and these points, and it's completely mysterious until 4 years later, when you've already learned everything else, you come back and you say, ah, yes, that makes sense. At least that was my experience. But it would be really sweet for us if we could get a similar description for A1 in the Tambara world, whatever that means. And so the first step is to say, what does that mean? What would it mean to have A1? A0 was pretty easy to understand because, A0 is spec of the initial object. And we know what the initial object is, it's called A underline. I said that before. The spec of A underline is what we should study. Great, that's how we do A0. For A1, we have to figure out what kind of Tambara functor corresponds to this guy, corresponds to adjoining a generator. And it turns out there's not just one Tambara functor, and that's a good thing. So let me now take a detour back into ordinary commutative algebra to describe what's going on with this ring Z adjoint T. Okay, so Z adjoint T as a ring is free on one generator. And that's also true as a commutative ring. It's the free commutative ring on a single generator. That's literally true. And what it means is that maps in the category of commutative rings from Z adjoint T to a ring R are the same as maps in the category of sets from a single point to the ring R, which, of course, is the underlying set of R. Okay. And maybe I should just be really explicit about this. There's a free forgetful adjunction going on. That's the underlying set of R. That's the underlying set of R. U is the forgetful functor from commutative rings to set. Okay. And this property that Z adjoint T co-represents the underlying set functor uniquely determines Z adjoint T up to isomorphism by the Yoneda lemma. That's one of our favorite lemmas. So Z adjoint T is completely specified by this property that what maps from Z adjoint T to R just recover the underlying set of R. And there's a little bit more going on. Whenever I started with a commutative ring R, the underlying set of R comes equipped with a commutative ring structure, right? It's not just a set. I started with R, which had an addition and a multiplication. So what's very interesting is that this co-representable functor, co-represented by Z adjoint T, well, these Hom sets are sets, but it turns out for Z adjoint T, these guys always have the structure of a commutative ring. This set of morphisms has the structure of a commutative ring because the underlying set of R has the structure of a commutative ring. And what that means in fancy words is that Z adjoint T is a co-commutative ring object in the category of commutative rings. That's just a fancy way to say the same thing. This always has the structure of a commutative ring. But if we unpack that, what we have saying that this guy has a ring structure means that there's like an addition map. UR cross UR to UR. There's an addition map there. And that addition map by the Yoneda lemma corresponds to some kind of function from Z adjoint T, some kind of ring homomorphism, from Z adjoint T to Z adjoint T tensor Z adjoint T. And this is maybe called co-plus. All right, this correspondence happens because UR cross UR will be the product of these two Hom sets, which is the same as the Hom from the coproduct of two copies of Z adjoint T. The coproduct in the category of commutative rings, is the tensor product, and things change directions because of the Yoneda lemma. So having this addition structure on the output set is the same as saying that I had this single co-plus operation on Z adjoint T. That single co-plus operation on Z adjoint T induces the addition operations on every commutative ring. And you can do the same thing with multiplication. There's also a co-times operation from Z adjoint T to Z adjoint T tensor Z adjoint T, which encodes sort of the multiplication operation in every commutative ring simultaneously. And in the category of Tambara functors, there will be a similar kind of thing going on. And what we're looking for in the category of Tambara functors is some kind of co-G Tambara object in the category of G Tambara functors. That's the sort of data we're looking for. If we could find such an object, it would come equipped with some kind of like co-structure maps, which would induce the ordinary structure maps on every Tambara functor simultaneously. We want this co-G Tambara object, which co-represents the identity functor. That's what Z adjoint T did. The functor co-represented by Z adjoint T is the identity functor on commutative rings, if you remember the co-commutative ring structure on Z adjoint T. Okay. Either that was like very chill and fun or extremely confusing for no reason. But let me say what this ends up looking like in our case. So if we want something which co-represents the identity functor from G Tambara functors to G Tambara functors, I want to recover for each Tambara functor all of the different levels of my Tambara functor. And so I need, in particular, some way to take a Tambara functor and get each of its levels. And the way that goes, well, let me say it this way. What I'd like is to have some kind of free forgetful adjunction to use. Here, just like we did over here, saying, oh, I want the set R, I want maps from a point to R by a free forgetful adjunction that should come from something like this, a free commutative ring on a single generator. I want a similar story to happen with my Tambara functors. And the good news is that there is a thing to put here. This functor is co-representable. There is a free construction. And the thing we put here, by definition, I call underline A join G mod H. The underline A, that's our initial object in the category of G Tambara functors. And adjoin G mod H to say, I'm freely adjoining a single generator at this level. So that maps from here to T are the same as maps from a single point to T of G mod H. Great. Okay, so this object exists. You can construct it in various ways. And if I had two different levels, did I do my picture the right way around this time? Yes. Great. So again, if K is contained in H, then I'm supposed to have this restriction, transfer, norm. Like so. And this restriction map is a function from this set to this set. And it's natural in the Tambara functor T, which follows from the fact that morphisms of Tambara functors respect the restriction. And all I need to say there is that I have a natural transformation from this Hom set to this Hom set. It's natural in T. That natural transformation is called restriction. This map here, which is the same as this map here. Okay. That restriction map is a natural transformation, and so it comes from some co-restriction map. Like so. Okay. So you can do the same thing with transfer and the same thing with norm. There's a co-transfer map, which looks like it goes the wrong way. And a co-norm map parallel to the co-transfer map. And there's likewise, there was an action of a Weyl group on here. That gives me an action of a Weyl group on this set, still a natural action, and that gives me a co-action on this on this Tambara functor. Okay, so all of the data of a Tambara functor was a bunch of commutative rings, a bunch of maps between them, and these actions and all the axioms. And all of that data with all the axioms that tie them together is sort of bundled up into these universal maps, this like co-restriction map, this co-transfer map, this co-norm map. These are single maps that somehow encode all of these operations for all Tambara functors simultaneously and the axioms that relate them. So understanding the collection of these objects, these A-adjoined blanks, and all the co-restriction, co-transfer, co-norm maps and the co-actions and how these relate to each other, that gives us a handle on A1 in the same way that understanding Z adjoined T with the co-plus and the co-times and all of that gives us a handle on A1 in classical commutative algebra. Yes?
You still have a co-plus.
I sure do. Yes, absolutely. Right. Each of these levels is a commutative ring, and so I also have a co-plus and a co-times and all of that stuff. Yeah. Cool. Yeah. All right, so I should next talk about like, what did we actually do? But before I get there, questions, comments, thoughts, feelings, etc. Yeah.
The analog of Z adjoint T is not just one Tambara functor.
Yes.
And so what's the spec of it and also the system of specs?
Great question. I don't know. So I don't have a definitive answer for you on what should spec of this thing be, but something you could do is take spec of each one and look at what the maps between them do, and we compute all of this in the paper. So yeah, it's a great observation. In classical commutative algebra, Z adjoint T is one ring, very nice. You can look at spec of that ring. It's a single topological space, very nice. It co-represents the identity functor just as a single object. We're very happy. Over here, I need a whole bunch of objects and a whole bunch of morphisms between them just to encode this same thing. And now I have a whole bunch of Tambara functors, and I could take spec of each one, and we do in the paper. We compute spec of each one, and we compute what do these co-norm, co-transfer, and co-restriction maps do between the specs. And all of that data we managed to compute, but it is, maybe slightly unsatisfying because it'd be nice to have a single thing that is A1. Okay, but yeah, in the paper we do, the thing we name A1 is this sort of diagram of spectra of Tambara functors. Yes.
Then you can forget it and then you can forget to functor it.
I don't know. Yeah. Yeah, it would be nice. Yeah. I mean, it is. So when you do spec of all these things, you end up with a Tambara functor valued in, well, okay, you have to be a little careful. You get a diagram of specs of Tambara functors, and there's a restriction and transfer and norm map between them that go the opposite way of the co-restriction, co-transfer, and co-norm maps, and they satisfy the same sort of composition relations that a Tambara functor would satisfy, because, well, the composition, well, these maps compose in the same way that Tambara functor maps do, and then you dualize everything. So you get a diagram that looks like a Tambara functor built out of spaces that are the specs of these various levels.
The Tambara functor, like an algebraic group, is to a group.
Yeah, that's right. Yeah, it's an algebraic Tambara functor, you might say. Okay. Cool. So, all right, so I mentioned that in the paper we learn a lot about all these objects. We compute spec of each one of these guys, although when I said that, I was kind of lying. For this A1 computation, when we actually compute spec of all these guys, we do it only for the case G equals CP. So I'm going to focus on that case from now on. That was already hard enough. So for G equals CP, there's only two of these free guys to think about. I can adjoin CP mod E, and I can adjoin CP mod CP. And I have my co-restriction go like this, and my co-transfer goes like this, and my co-norm goes like this, and I have my like co-action of the Weyl groups and everything. Great, and so I have this picture in the category of Tambara functors, and I could take spec and get a picture in the category of topological spaces. And the way we went about actually computing what's going on here, what are the primes in these guys, is, well, we needed some commutative algebra tools. The way you understand Z adjoin T is you use commutative algebra. Just trying to think off the top of your head of what should the prime ideals of Z adjoin T be is kind of hard. Like Z you can understand, oh yeah, it's tautologically true that the prime numbers give me the prime ideals of Z and also 0. But for Z adjoin T, you have to like do something. And so we did something, and the key tool that we ended up using was a going up theorem. And so the going up theorem actually works for all G. So maybe I'll put the G equals CP over in this box. Here's the picture when G equals CP. This is the picture we studied in the paper. But the going up theorem we have for arbitrary finite groups G. And in ordinary commutative algebra, what the going up theorem says is that if I have an integral morphism of commutative rings, then I get some nice picture on specs. Maybe I'll draw it suggestively. If I have a map from A to B, which is integral of just commutative rings, then I can get a map from spec B down to spec A, and the going up theorem says that this map has sort of a path lifting property, or maybe I'll describe what I mean. If I have a point upstairs which maps to a point downstairs, and I have an inclusion of a point here into a point here, then I can find an inclusion of a point here into a point here. I can lift the path. That's what's going on. But if you don't know the going up theorem, then this probably won't be helpful. And if you do know the going up theorem, then that was useless. And so I'll just tell you, it's a useful theorem from commutative algebra if you want to understand like spec of a number ring, all of these sort of rings of integers of Dedekind domains in general. You really want to understand the going up theorem. That's the best tool we have for starting to study these kinds of objects. And for Tambara functors, we proved a very similar theorem. So if T to T prime is a levelwise integral morphism of G Tambara functors, then it satisfies going up. And also, if it's furthermore injective, then it also satisfies the lying over property, just as with that same thing that happens for commutative rings. And this lying over property is quite nice. It says that the map on spec is surjective. So the upshot of the whole thing is that whenever I have a levelwise integral morphism of Tambara functors, so it's a morphism of Tambara functors at each level, it's a map of rings. If all of those individual maps of rings are integral maps, then the induced map on spec satisfies this going up theorem. And if all those maps individually were not just integral but also injective, then the induced map on spec is surjective. And that's very handy, because if we're in a situation where I have a Tambara functor that I really want to know about, like let's say this guy, I want to know spec of this guy, and I have no clue. What I would love to do is build some kind of integral extension to something else, and then get a map, spec T prime, surjecting onto spec A adjoin CP mod E. And if I could understand the points here, then I would know all the points here. Great, pretty basic tool. And then the question is just, well, how do I build a good integral extension to something, right? I want to put something here where I could understand this side of the story, and I'm guaranteed to have an integral extension, right? And so that's where our second big tool came into the picture, and that's the ghost construction. Right, okay, so now I think I've said all the words in the title. Tambara Affine line going up for ghosts. We're here. And the point of the ghost construction is to give us examples of these integral extensions that we can use to compute specs with. The ghost construction we really only did for G equals CP. matrices. Okay. So what is the ghost construction? It's a functor called ghost. I should put a CP here. It goes from CP Tambara functors to CP Tambara functors. And this functor has very nice properties. It's actually not just a functor, it's actually a monad. And in particular, I have a natural map from T to its ghost for all T. And what's more, this natural map is always integral. It's always a level-wise integral morphism of Tambara functors. And it's not always injective, but its kernel is always nilpotent. And that's enough, okay, turns out. So, in particular, this induces for us a natural map from spec of the ghost of T to spec of T, which is always surjective. Nilpotent kernel is close enough to injective for this to work. And so if I could understand these guys, then I could understand these guys. And the great news is that we can understand these guys. Okay, so I'll explain what actually the ghost construction is. What do you do to take a ghost, to CP Tambara functor and construct its ghost? So I started with a CP Tambara functor. Well, there are two reasons. First of all, it behaves a lot like the table of marks for the Burnside. So maybe I should say, if you do the ghost of the Burnside, I end up level-wise with the table of marks, and the restriction, transfer, and norm do whatever they should do on marks. And the map from the Burnside to the table of marks is sometimes called the ghost map. So that's one reason we called it the ghost. It's a construction that sort of builds something like the table of marks for an arbitrary Tambara functor. And the other reason is that it was really fun to use a ghost symbol. Oh, sorry, say again? Yeah, we, for no reason in particular, we posted this on the archive on October 31st. He figured it out. It was Mike's dad's birthday, that's why. And so, okay, right, so it's a nice symbol. If you want to use the exact symbol, I have it as a tech package that you can request from me. But that's a bit silly. It was just fun to do. So I have a CP Tambara functor. It has this sort of structure. And there's an action of CP on this level. And now I'm going to produce the ghost of T. So at the bottom level, the ghost of T is exactly the same as it was before. In the ghost of T, the bottom level is just the same ring I had before with the same CP action. Everything's exactly the same. At the top level, I put something different. And that new thing is I take the CP fixed points of what I had at the bottom. There was a CP action on this level. And I also take, I will write it the way we do in the preprint, and then I'll explain what this means. These CP geometric fixed points of the Tambara functor. And what that means is I take the CP mod CP level, that top level that I had, and I mod out by all the transfers from the lower level. Take the image of this transfer map, okay. The image of that transfer map is always an ideal of this ring, you can prove. And so this quotient is a ring, and that's what this guy is. Great. So I can build this guy. The restriction map is just project onto the first factor. Oh, I did my arrows backwards from how I like to do them. Transfer and norm on the right. Okay. This transfer map is you like take something here. I either do transfer and then restrict to get back to where I was. Start here, transfer, restrict, now I'm back here, but I had a CP fixed point. Or in the second component, I do the ordinary, I do 0, because I do the ordinary transfer and then I mod out by transfers. And then this norm map, I do the same kind of story, norm and then restrict. So I start here, I go norm, restrict, now I'm back here, but I had a CP fixed point. Or to go to this factor, I just do norm. Very nice, okay. It all works out very well. This guy has a lot of really nice properties, but it's just amazing that it really works so well. You can compute a lot with it. Like once I've modded out by these transfers, this norm map turns out to be a ring homomorphism, which is very convenient. And the upshot of all of this stuff is that I can really understand what is spec of the ghost of a Tambara functor. We can really give a description of this guy, almost. So this is isomorphic as a set to a disjoint union of two things. I have spec, ordinary spec of the CP fixed points of the bottom level, and ordinary spec of these geometric fixed points. And somehow every Tambara prime ideal of this guy comes from either an ordinary prime ideal of the fixed points of the bottom level in my original Tambara functor, or an ordinary prime ideal of the ring I get by taking the top level of my original Tambara functor and modding out by transfers. And you can just sort of compute all of those things, at least if you understand these two rings well enough. And these two computations, these are ordinary specs. So you can use all of your commutative algebra tools. You're dealing with ordinary rings, you want to understand their prime ideals. You can do localizations and going up and going down and all of your tools willy-nilly. Talk to your favorite algebraic geometer, see what they can do for you. And you get a nice description of the elements of this set. Very nice. And that gives you, for example, an upper bound on how many primes there are here. Cool, okay. This is certainly not an isomorphism of topological spaces. It is an isomorphism of sets, but the other good news is that if T is Noetherian, then so is its ghost. And by Noetherian, I mean ascending chain condition on Tambara primes. And the topology on these spaces is determined by just the inclusions between prime ideals. You don't have to do anything fancier. So I have my set of points. If I could understand the inclusions between the primes corresponding to these points and the primes corresponding to these points and between them and so on, then I would understand the full topology of this set. And so that's what we actually ended up doing for spec of this picture up here. We took these CP Tambara functors, this free guy, we built their ghosts, we did commutative algebra to find all the prime ideals in there, we figured out which ones were contained in which other ones, and then we just put the picture together, we figured out what co-transfer and co-restriction and so on do. And in general, even if you weren't going to do this exact picture, if you had some CP Tambara functors to study and you wanted to know what's up with their prime ideals, you have this general plan. You look at, you build the ghost, you figure out spec of the ghost by this kind of construction, figure out the containments between the primes. Then you figure out, this map is surjective, but it's not always injective. So you have to think about, okay, if I had two different primes here, did they collide when I went here? And that's usually not so bad to figure out. And then you have a complete listing of all the primes here and hopefully how they're contained. And then you determine this entire topological space. A reasonably mechanical procedure, although sometimes pretty long and tedious. Okay.
You can do that for any magnitude, right? Like you can generalize that construction and you're still going to have a map from T to the ghost, right?
This is a work in progress. We think so. But it's not so easy to immediately write down exactly what it should happen at each level. Okay, yeah, maybe. We should talk.
Rationally, that's going to be an isomorphism. cover always going to be between these maze splitting junction be right or wrong?
Okay. Well, yeah, we should talk about it. Yeah, so far, I've had trouble trying to write down a specific thing that clearly works. But if there is a very easy specific thing to write down that clearly works, that would be great. Yeah. But in this paper, to go beyond CP, just computing specs of these guys would get pretty ridiculous. And so we just focused on CP and we were able to write something down. But I would love to do something more general. This is David and I and some other collaborators have been thinking about this, and we don't have a brilliant con extension idea. So it would be great to talk. Yeah. Okay. Yeah. Other questions? Yeah.
Can you tell us what sorts of rings appear in these A underline?
Yeah, I sure can. So the A underline CP mod E is a little ridiculous. The A underline CP mod CP is not as bad. So maybe I'll put this here. So I'm adjoining a generator. I'm freely adjoining a generator to the fixed point level. At that level, I would have already had Z adjoin T mod P squared minus PT. And so I'll still have that T. I'm going to have my new generator X, and I'm going to have the norm of the restriction of that generator. It turns out that's all you need. And then you have some relations. You have T squared minus PT. You have T times N minus T times X to the P. And I think I might have done it. I think that's all we need. Thank you, David. And at the bottom level, very nicely, it's Z adjoin X. It's the restriction of the generator you had here. And I've described what the things are. The T is the normal T from the burn side. The X is the new generator. The N is the norm of the restriction. And the X is the restriction of the X. And so you can figure out all the maps from there. Yeah. And the CP mod E case is more ridiculous because you start with your generator at the bottom level. It has freely adjoined Biel conjugates. Those guys all have transfers upstairs. All those transfers are ridiculous. It's a crazy ring, crazy pair of rings. And the fixed points of the bottom level end up giving you like CP cyclic polynomials, cyclically invariant polynomials. It's a nonsense kind of story, but you can write it down. And you can look at it in the preprint. So, okay, cool. So I guess oh yeah, sorry.
Oh, I don't know, we're just doing questions now.
Well, we can feel free to do questions now. I have like more things to ramble about, but please do ask a question.
I'll save it to you.
Okay. Right, so we did all of this for these free guys. We wrote down descriptions of spec of this guy, spec of that guy. What do all these maps do between the specs? We have that complete description for CP. We proved this going up theorem in general, the lying over consequence. I should mention that in commutative algebra, if you're a commutative algebra junkie, you'll know that there's one more thing that happens for integral maps, which is incomparability. And that really notoriously does not happen, not notoriously, we're like the only people who thought about this. But it does not happen for Tambara functors. It really doesn't happen. And maybe a really good picture to think about here is A underline itself, which is like the relative of the integers, the initial object in the category of Tambara functors. This guy has a ghost, which, as I mentioned earlier, is really the table of marks at each level. And if we're doing this for CP, spec of the ghost, well, it's actually pretty easy to tell what it should be. If you think about that description over there, you see it's going to be 2 copies of spec Z, at least as a set. And it turns out as a topological space, it's not so bad. It's 2 copies of spec Z with inclusions from each point on bottom to the corresponding point on top. That's spec of the ghost of A. And spec of A was originally computed, I think, by Nakaoka in the CP case. Looks very similar except that something collapsed. And we collapse the point, in fact, at the prime p. And so I do get a surjection from here to here. And you can work out the topology here from the inclusions, and you can work out the topology here from the inclusions, and you can do the whole story. And over this point P lie these two different points, which are not incomparable. There's an arrow from one to the other. The incomparability theorem fails for Tambara functors. But otherwise, integral maps and integral extensions behave about as well as you'd hope. And because of that, we're able to not just compute specs of these guys, but also we can figure out their dimensions, the Krull dimensions of these spaces. How long can chains of inclusions of prime ideals get? By just bounding the Krull dimensions of these various pieces and understanding the containments between things. So we're able to compute Krull dimensions of CP Tambara functors pretty easily. We're able to find specs of Tambara functors, CP Tambara functors pretty easily. And I should mention a few other things that we do in the paper. So I mentioned this construction earlier, this FP functor from G commutative rings to G Tambara functors. And it's the Galois theory construction. I take a commutative ring with G action, and I look at the fixed points of that ring. Those give me my different levels, and I have my normal Galois theoretic inclusions and transfers and norms between those. And we compute also for arbitrary G that if I take a ring R, I get just the ordinary prime ideals of the G fixed points of R. And so this is some kind of story, if you like. This is the GIT quotient of spec R by G. And it's saying something about how G Tambara functors are some kind of deformation of G rings. If I just have my fixed point Tambara functors, I'm just encoding like rings with action geometrically. But there are other things in this category that are not just G commutative rings. And the GHOST tool lets us study all those things. Like these guys are not fixed point Tambara functors, but they do have interesting spectra, and those prime ideals and the relationships between those prime ideals induced by co-restriction and co-norm and co-transfer tell us things about the behavior of Tambara functors in general. Okay, so I think I'll stop advertising random features of the paper now. Thanks for listening. Yeah.
More questions?
I guess I have two questions. The first one is like your notation A underline bracket something makes me think that maybe I should be thinking of that as like G mod H many copies of the A underline. Is that does that have?
It's not exactly G mod H many copies of A underline, but the way we should read this is that if I do this should be A with one freely adjoined element at level G mod H. But it's also, if you like, A with the G set G mod H freely adjoined, if that makes sense.
Reading it more as like a polynomial.
Yes.
Okay.
Yeah, this is like a join a polynomial generator at level G mod H, or adjoin the G set G mod H if you like, because when I adjoin a generator at level G mod H, I also have to adjoin its Weyl conjugates, or I adjoin something and then it has Weyl conjugates. And if I freely adjoined it, I don't have anything to say about those. I have to adjoin a whole bunch of things.
And my other question was, could one contemplate similar kinds of questions for green functors as opposed to Tambara functors?
I think one could.
Okay, but I guess you chose Tambara because they were more structured and behave better. Or...
Yeah, yeah. Green functors. So like something that's very nice about Tambara functors is that I have these norm maps that go up. It's sort of a blessing and a curse. On one hand, they're really annoying maps because they norm of A plus B is really hard to deal with. But on the other hand, the norms have to send 1 to 1. So if I have an ideal of a Tambara functor and I find the element 1 sitting at any level, then by restriction it also sits in all the lower levels, and by norm it also sits in all the higher levels, and by restriction and norm together it sits in every level. And so As soon as you have one at any level in an ideal in a Tambara functor, it propagates everywhere and your ideal is the entire Tambara functor. And that's really not the case for green functors. For green functors, I can have ideals that are the unit ideal at many levels and then stop being the unit ideal eventually. And it's like, I don't know, then I get very confused. It's nice to have a situation where your prime ideals never contain one, and it feels like sort of you get to control things from different levels at the same time.
I guess we kind of want an edge of that story.
Yes. Yeah, so certainly there's these like compatible pairs of n-infinity operands, and you can think about things in between green and Tambara and beyond, but I haven't, so yeah.
I also can ask that green functor, but let me ask it differently. I mean, you drew the picture of spec of Burnside ring.
Yes.
Or spec of a underline. Is that an overall G? The Tambara spec is the same as spec of Burnside ring?
Great question. We don't know. Work in progress. And so in our work in progress, we can say this is true for nilpotent groups. Don't quote me on this too hard because maybe we made a mistake. But that seems to be the case, and maybe hopefully all groups. But there is an important distinction to make between the two pictures. So if I just think about the Burnside ring of CP, spec of this is two copies of Z joined at a point, absolutely. There's my point P. But if I do spec of the CP Burnside Tambara functor, there's a slight difference in that I have inclusions here. Each prime is included in the corresponding prime up here. And so the curl dimensions of these two spaces are different. This has dimension 1, and this has dimension 2. And there should be something similar happening for other G. But the set of primes, there should be a way to write down a bijective correspondence, at least a lot of the time. Yeah, thanks.
The definition of the ghost construction, you instead, I mean, there's this, I guess it's the Adams transfer equivalence here, that you can describe CP fixed points as the callback of homotopy fixed points and geometric fixed points along the construction. And you're basically, instead of taking the fiber product, you're taking just the product.
Yeah.
So it feels like there should be a fiber sequence where the third term is kind of a tape, which at level H is a H tape spectrum.
Yes.
Is that part of your story?
I think we thought about this briefly.
You try. Is it? Because that would sort of tell you how what gluing is happening when you're going from spec to those. And it would, and this diagram also sort of suggests what happens for larger groups, and in particular, if you're looking at bigger groups, it would typically be that might be why rational effects are simpler, because they're taking homotopy orbits for the normal normalizers, and things like those are not going to contribute rationally integrally.
Yeah. Yeah, I wish I could say something useful, but it would be nice to understand that story. Yeah.
So the spectra of the Mark functor is vector and affine. So is that acceptable? Oh yeah, what?
Here's the sad news. We don't have a structure sheaf. So it's a topological space, and it's in the paper we show it's sober. It has all the nice like topological space properties that an affine scheme should have, but we don't have a good way to construct a structure sheaf. If you have a thought, I would love to. I would love to think about this. Yeah. Yeah. Right. So it would be nice to say like, oh, a Tambara affine scheme is like it's an object of Tambara opt. But to make this picture useful in commutative algebra, what you need to know is that there is a structure sheaf on each spec of R, and when you have a morphism of ringed spaces, it actually corresponds exactly to a morphism of commutative rings. And that's the key piece that ties the geometric and algebraic stories together. Is I have a geometric sheafy description of what's going on with morphisms between rings, and I have an algebraic description of what's going on with morphisms between rings, and they're the same story. And I only have one half of this picture, and so I can try to like formally produce the other half, but it doesn't give me a new insight, I think.
Thanks again.